Good morning. Today we're going to cover two sections, section 3.9 and 3.10, but don't worry, 3.10 is short. That's why I've just tacked it on to the end of this presentation. So you're only going to have one video today. Granted, it might be a long one, but you'll only have the one. So to start off with, we're going to cover section 3.9, derivatives of logarithmic and exponential functions. So let's first talk about the properties of the natural log of x and the function e to the x. E to the power of the natural log of x is just equal to x for all x greater than 0. And we say this because we're putting x inside of the natural log function. And you'll see on the next slide that the natural log function can only accept values greater than 0. So we can't include 0, but we can go all the way up to positive infinity. That being said, the natural log of e to the x is equal to x for all values of x. And this is because we can put whatever value we want into e to the x and we'll still get a positive value out and be able to plug that into natural log of the natural log function. Next, y equals the natural log of x if and only if x is equal to e to the power of y. So then we get the e and the ln canceling each other out and we get y equals y. Next, we've got for real numbers x and b greater than 0, b to the power of x is the same as e to the natural log of b to the x, which is the same as e to the x times the natural log of b. And how are we able to do that? Well, you'll see in the next 3 bullet points, we've got some properties of the natural log function. The natural log of a plus the natural log of b is equal to the natural log of a times b. We also have, conversely, that the natural log of a minus the natural log of b is equal to the natural log of a divided by b. And finally, the natural log of a to some power b, we pull that power out in front and we get the natural log of a times our value b. So those are the properties that we're going to rely on in order to find some derivatives of the natural log of x and a few things like e to the x. So let's talk about the derivative of the natural log of x. On the right-hand side, I've drawn in black y equals the natural log of x. And you can see that we cross 1 when x equals 1, we equal 0. That's very important. You should always remember that. So we have the natural log of x drawn in black, and you can see it's got values tending towards negative infinity as we approach 0, but it never crosses that line. It never equals 0. So we're never allowed to put 0 into our function, but we can put values greater than 0 in. So 0.0001 is completely valid. It's just 0 that is not valid. So d dx of the natural log of x is equal to 1 over x. And that might be surprising, but there's a proof that I'm choosing not to present to you because proofs are kind of tedious and don't really help you understand things too much. But this is our answer, and this is going to be for all x greater than 0. But if we are saying, hey, I've got a problem where I can't put in negative values, well, we can always take the absolute value of whatever's going on inside. So d dx of the natural log of the absolute value of x is equal to 1 over x, as long as x doesn't equal 0. So our domain in this case is negative infinity to 0, excluding 0, and then 0 to positive infinity. Now we can be even more general, and if u is some function and it's a differentiable function at a point x, and u of x does not equal 0, then d dx of the natural log of the absolute value of our function u of x is equal to u prime divided by u. And this is going to come in really handy while we do some examples in the next couple slides. So first off, let's try and take the derivative of y equals the natural log of 4x. And you can go ahead and give this one a shot on your own. Welcome back. So the first way that we can do this problem is using the chain rule. So using the chain rule, we're going to take the derivative of the outside times the inside left alone times the derivative of the inside. So the derivative of our outside is just 1 over whatever's on the inside. So we've got 1 over 4x times the derivative of the inside, which is just 4. Well, our 4 and our 1/4 are going to cancel out, and we're left with just 1 over x. Now, there's another way that we could possibly do this problem, and it's by using our logarithm rules. So earlier I presented that the ln of a plus the ln of b is the same as ln of a times b. We can undo that. We can unwrap that. So the ln of 4x is the same as ln of 4 plus the ln of x. When we go to take our derivative, we just use the sum rule, and we have d dx of the natural log of 4. Well, the natural log of 4 is equal to some value. That's just a number, and the d dx of just a number of a constant is equal to 0. So we get 0 from that term, and then we're just left with d dx of the natural log of x, and we know that to be 1 over x. So 0 plus 1 over x is just equal to 1 over x. Our answers match from one example to a different way to do the same example. So let's try something a little bit more challenging. Now, instead of just x or 4x or some polynomial, we've got a function secant of x. So secant can have positive and negative values. So we're just going to take it the absolute value. So find dy dx for y equals the natural log of the absolute value of secant of x. So go ahead and try this. I believe in your ability to at least set this up and then come back and meet me and see how far you've gotten. Welcome back. So using the chain rule, we're going to take the derivative of the inside, which is just going to be, the derivative of the outside. So ln of something is equal to 1 over that something. So we get 1 over secant of x times the derivative of the inside. The derivative, the derivative of secant of x is equal to secant of x times tangent of x. So we're left with secant of x times tangent of x, all divided by secant of x. Our secant of x terms are going to cancel out, and we're left simply with tangent of x. And this might be a little surprising. You might have expected to get some sort of natural log in your answer or 1 over something in your answer, but it just shows sometimes you just have to work out the problem to see what it looks like. So now let's talk about things of the form b to the x. So as long as b is greater than 0 and does not equal 1, then for all values of x, d dx of b to the x is equal to b to the x times the natural log of b. And in this case, we talk about b being some number. So maybe it's 3, maybe it's 15, maybe it's 1,000, but it is a number. So if you see something that looks like 3 to the x or 10 to the x, this is how you deal with that problem. So let's do an example. Find the derivative of g of t equals 108 times 2 to the power of t divided by 12. So this one's a little complicated. We've got a constant multiple out in front, and our power is t divided by something. So we're going to have to pay special attention to that. But go ahead and give it your best shot and see how far you get. Welcome back. So like I mentioned before, we've got a constant multiple. So let's start with that constant multiple rule. G prime of t is equal to 108 d dt of 2 to the power of t over 12. And now we're going to have to use the chain rule. So let's go ahead and take the derivative of our outside function, which is 2 to some power, and we're going to get the natural log of 2 times 2 to the power of whatever. And that whatever ends up being t to the t divided by 12. And then to finish it up, we want to take the derivative of our inside function. And our inside function is t over 12. So we're looking for d dt of t over 12. Well, we've just got t times 1 over 12. The t is going to go away, and we're left with 1 over 12. So all in all, we're left with 9 times the natural log of 2 times 2 to the power of t divided by 12. So now we've talked a lot about the natural log, which is log base e, our exponential function, e as in the number e. But what about log, just our regular, degular, schmegular logarithm function? So if b is greater than 0 and b doesn't equal 1, then d dx of log base b could be 10, b could be 15, b could be e, of the absolute value of x is 1 over x times ln b for x not equal to 0. So let's take another example. Compute the derivative of t of x equals n log base 2 of n. Go ahead and see how far you can get and then come on back. Welcome back. So using the product rule, we're going to have the derivative of the first, which is n, so we just get 1 out of that, times the second term, which is log sub 2 of n, plus the first function times the derivative of the second. Now log base 2, we're going to end up with the natural log of 2 in the denominator times the inside, which is just n. So we get an n on top and an n on bottom. Those are going to cancel out. And our final answer is going to be log base 2 of n plus the natural log of 1 over the natural log of 2. So now that we've talked about that, let's go ahead and finish up with our second section for today, section 3.10, derivatives of inverse trigonometric functions. Now, there's a lot that I could show you here, but really the proofs are just going to be more confusing than they're going to be helpful, and there's not much more to this. So I'm just going to present these to you and speak them out in case you're writing them down. But go ahead and write these down. These are just ones you're going to have to either memorize or that's really it. But they usually don't come up too often in Calc 2. I've never come across them in an engineering discipline or a math discipline. These are just ones you're just going to have to know. So d dx of sine inverse of x is 1 over square root of 1 minus x squared. d dx of cosine inverse is just the negative of the previous one. You'll find a pattern here. d dx of inverse tangent of x is 1 over 1 plus x squared. d dx of inverse cotangent is the negative of what I just said. d dx of secant inverse of x is 1 over the absolute value of x times square root of 1 minus x squared, and d dx of the cosecant inverse of x is the negative of what I just said. And that's going to be it for today.